Welcome back. This is the first of several presentations where we're going to introduce some further differentiation rules that go beyond the power rule and differentiation of polynomials, and which we will then put to use to show how, on one hand, how the differentiation rule works, and how, on the other hand, we can reinforce the various ideas that can be computed with calculus. So let's take a look at the product and the quotient rule here. We need the product and the quotient rule basically because there are certain products like e to the x times x squared plus 2 which cannot be multiplied out, like products that you may have seen as you were working with the power rules, such as x cubed times x squared plus 2, where the idea is, well, first multiply out the parentheses and then apply the power rule. Similarly, quotients like rational functions, so like 2x squared plus 3 over x squared minus 4, they cannot be converted into functions that don't involve quotients, and so we need to have rules that allow us to just differentiate abstract products and quotients of functions. What should they look like? Well, it's very tempting after the sum rule to hope that you can just move the derivative inside, and this slide is just designed to make sure that we don't think that, because we must be really careful here. The derivatives can't be moved into products and quotients. If we take, for example, g of x equals x cubed and k of x equals x squared plus 2, well, then the product of g and k is x cubed times x squared plus 2. If you multiply that out, you get x to the 5th plus 2x cubed. And the derivative of that is, of course, 5x to the 4th plus 6x squared. And that's not equal to the product of the derivatives, because the product of the derivatives would be 3x squared times 2x. And, well, that's 6x cubed, and that's certainly not this expression up here. Okay, so we need to go back and think about how to derive the product rule. Again, this is the idea behind proofs, essentially. Even though mathematics is often presented as here's a theorem and here's the proof typically exists before the theorem, or sometimes definitely exists before the theorem, because the proof in some way leads up to the theorem, and that's the case for the product rule. So the only way we know how to really compute derivatives, even though it's not terribly pleasant necessarily, is the difference quotient. And so, just like any derivative, the derivative of a product g times k prime is just the limit as h goes to 0, gk of x plus h minus gk of x divided by h. So how do you work that out? Well, first of all, you resolve the product, right? gk of x plus h is g of x plus h, k of x plus h, and gk of x is g of x, k of x. And now what we're looking for would be difference quotients that use g of x plus h minus g of x divided by h, and k of x plus h minus k of x divided by h. And, well, we can't work that out with this expression because we can't factor out any common terms. But if we had an extra term, say, g of x times k of x plus h, then we could factor out a k of x plus h. And that's exactly the idea for the proof. The only thing that happens in this step, even though it may look a little bit intimidating, is, remember, there are two tricks in mathematics, adding 0 and multiplying by 1. Well, we've added 0 here, right? These terms just add up to 0, and it's just that these terms happen to work out in such a way that we can factor things out nicely. And this is, again, something that you would be training in detail in a proof class. Here we're just doing this for background. But what we can see is that in the first terms, let me capture it all here. In the first terms, we can factor out a k of x plus h, and in the terms at the end, we can factor out a g of x, and that's nice because that leads us to the limit as h goes to 0 of g of x plus h minus g of x quantity times k of x plus h plus k of x plus h minus k of x times g of x, quantity times g of x divided by h. And here we can see that we've got a difference quotient for g because this thing is divided by h, and we've got a difference quotient for k because this thing here is divided by h. So we can puzzle the fractions apart. We get the limit as h goes to 0 of a difference quotient for g times k of x plus h, plus a difference quotient for k times g of x. And we can pull the limits inside now, because the limit laws allow that. And, well, then we can see the limit of the difference quotient for g gives us g prime of x. The limits of k of x plus h will be k of x. The limit of the difference quotient of k gives us k prime of x, and the limit of g of x is just g of x. So the derivative of the product gk prime ends up being g prime times k plus k prime times g. And the derivation of the product rule, of the quotient rule, is indeed quite similar, so we'll forego that part. Remember, these derivations are for background information. We want to know where this stuff comes from. We want to realize that no, this is not something that somebody arbitrarily wrote down. This can be justified. But in the end, the idea of a calculus class is to apply these rules, and that's where we're headed. So first, let us just summarize these rules. The theorem is about the product and the quotient rules. And if you've got a product P equals G times K and a quotient Q equals G over K, where G and K are differentiable at the point X, well then the derivative of the product is G prime times K plus K prime times G. And if K of X is not equal to 0, then the derivative of the quotient is G prime times K minus K prime times G divided by K squared. And the way to remember these is you want to make sure that you remember the product rule in the same order as the numerator of the quotient rule, basically because that way you don't have to worry too much about this negative sign in here, which I have seen get lost on many an exam, and typically it was because students remembered the product rule one way and then tried to remember the quotient rule the other way, and then things just got misfired. In fact, when I was a student, the only thing I memorized was the quotient rule, and I remembered the product rule is just the numerator with a plus. So there are many ways to help your memory out here, and the main thing is you just need to have these rules available as you are doing mathematics. You can also write these rules out verbally, and so for example the product rule simply says that the derivative of a product is the derivative of the first factor times the second factor plus the derivative of the second factor times the first factor. And that helps too, because if you try to just start naming a bunch of stuff, well, that's where we're running into this thing that I've talked about in the introduction to the course. Your brain has about 7 spaces for memory, and if you're using up 2 of those for new letters, well, then you've got only 5 spaces left to do the rest of the problem with, and that can clutter things up a bit, and so it can be very beneficial to not think of the product as a g times k, but as a first factor times a second factor. Similarly, it can be beneficial to think of a quotient not as g over k, but as numerator over denominator. And then the quotient rule says that the derivative of quotient is the derivative of the numerator, right here, times the denominator, minus the derivative of the numerator, the derivative of the denominator, sorry, times the numerator, and then we divide by the square of the denominator. So there are quite a few ways to keep these rules in mind, and the main thing is you find one that works for you, that lets you allow to compute these derivatives reliably. Now that we have them, well, let's just compute some derivatives. The simplest kind of problem in this setting now is to just say take a function, compute its derivative. So for example here we've got e to the x times x squared plus 2, and the derivative of that would be the derivative of e to the x times x squared plus 2 plus the derivative of x squared plus 2 times e to the x. And that's, of course, just e to the x times x squared plus 2 plus 2x times e to the x. And the only thing we can do here in the way of simplification is to factor out the e to the x. So we get e to the x times x squared plus 2x plus 2. Again, if you see a factorization in a derivative, you might as well go ahead and execute it, because from what we've already seen about calculus, a lot of times we're interested in the zeros of the derivative, and zeros are easier to find for a factored expression. But that does not mean we're just starting to run around and try to factor anything, just come what may. If we see one, we put it down. If not, we just leave the expression as is and simplify. Okay, what else can we do? Well, we can compute derivatives of quotients. Pretty much the same story, only that we have to use the quotient rule. So f prime of x here would be the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator divided by the square of the denominator. Typically we don't write this stuff down, even though at the beginning I'd like to give all the steps possible. Typically the first step is to already compute the derivatives in the numerator, and so you end up with the derivative being 4x times x squared minus 4 minus 2x times 2x squared plus 3 divided by x squared minus 4 quantity squared. And then really the only thing we can do here is multiply things out. I didn't even factor out the x here, I don't think. Yeah, this is just 4x cubed minus 16x minus 4x cubed, and then a minus 6x, and here we can see 4x cubed minus 4x cubed goes away, and we get a negative 22x in the numerator. So this is negative 22x divided by x squared minus 4 quantity squared. And yeah, the other good bit of advice here is that when you differentiate quotients, it is advisable to leave the denominator as a power, because typically we will, especially in graphing, we will be interested in also computing the second derivative, and it will be advantageous to have this as a power, because then we can apply the chain rule, and we will see a few cancellations that are helpful more easily than otherwise. So leave the denominator as a power. What else can we do with calculus? Well, we could compute equations of tangent lines, for example, for a function like x times e to the x, which looks rather harmless, but remember, we really need the product rule to differentiate this thing. Okay, so we want to find the equation of the tangent line of this function at a equals 1. What do we need? We need the derivative. The derivative is derivative of x, which is 1, times e to the x, plus x times the derivative of e to the x, which is e to the x itself, and so that's just e to the x times x plus 1. We need the derivative at the point where we want to compute the tangent line, so the f prime of 1 is just 2e, e to the first times 1 plus 1. We need the value of the function at the point, which should be just e, right? F of 1 is 1 times e to the 1, so that's e. And, well, then we can work out the equation of the tangent line, either with the point slope formula that you could memorize, or, as I would always recommend, just don't memorize too much unnecessary stuff. Instead, just get used to executing routine algebra. It's just math. The equation of a straight line is y equals mx plus b. The tangent line has slope m equals 2e and goes through the point 1e, which means we get that e is equal to 2e times 1 times b. Solve that for b, we end up with b being negative e, and that means that our equation of the tangent line is y equals 2ex minus e. Looks a little bit more complicated than other tangent lines we've worked out before, but remember, e is just Euler's number 2.71828182845945, and so on and so on. It's a lot easier to just work with e. We can also double check this problem by graphing the function and by graphing the proposed tangent line. Well, here's the function, here's the point where we wanted to compute the tangent line, and here's the line that we computed on the previous panel, and we can see that yes, this line ought to be correct because it really does look like a tangent line should look. Okay, we can also, by using calculus, determine where a function is increasing or decreasing, and with this being a rational function, we will need the quotient rule. So the derivative is, well, derivative of the numerator, 1 times the denominator, x squared plus 4 as a quantity, minus derivative of the denominator, 2x, times the numerator, x, divided by denominator, x squared plus 4 quantity squared. Okay, and that we just simplify, right? We get x squared minus 2x squared, that should be minus x squared, so 4 minus x squared over x squared plus 4 quantity squared, right? And we can factor that, because 4 minus x squared is 2 plus x2 minus x, or 2 minus x2 plus x. The denominator we can't factor because, in fact, the denominator does not have any zeros. So that already means that the derivative has a 0 at 2, a 0 at minus 2. It's defined everywhere, so we only have 2 critical points plus minus 2. So we set this equal to 0. 2 critical points plus minus 2. We do our number line. We have 2 critical points, negative 2 and plus 2. We need 3 checkpoints, and because 2 and minus 2 are so far apart from each other, we get nice checkpoints. We check at negative 3, at 0, and at 3. And we need to find the signs of the derivative. Well, let's see. The derivative at negative 3. What can we do here? The derivative, the denominator here, that denominator is always positive or non-negative, and in fact it's always positive, so we don't have to worry about it. So we really only have to worry about the sign of 4 minus x squared. Well, 4 minus negative 4 minus negative 3 squared is 4 minus 9, which is negative 5, so it's negative there. 4 minus 0 is 4, which is positive, and 4 minus 9 is negative again. So we get that the function should be decreasing, increasing, and decreasing. And again, we can double check that by simply graphing the function and comparing the graph to our analytical result. And this one I think I drew rather well to scale because, well, negative 2 is here and plus 2 is here, and we can see really the function is decreasing, increasing, and decreasing. I think that took me quite a while to just, make the adjustment, recompile, make the adjustment, recompile, and all that. But hey, it just helps to verify things. It's a good sanity check, and as I always almost literally preach, don't worry about the back of the book. Find ways to check your work that you can also execute when you are on the job or when you are taking an exam, if graphing calculators in this case are allowed on the exam. Okay, finally we're finishing out with a more complicated derivative that goes in the direction of getting us accustomed to the fact that sometimes these differentiation rules pile up, and this is another thing that I sometimes see being a bit of a cliff on a test, and that is that in an expression such as f of x equals x squared e to the x times x plus 1, people realize this is a quotient, but inside the quotient the numerator is another product, which means the derivative of this numerator must be computed with the product rule and no other way. And that is where sometimes people just jump a little bit too quickly and just take the product of the two derivatives, and of course that's wrong. So the derivative here is computed with the quotient rule, and within the quotient rule here, this derivative of the numerator, we can see, is computed with the product rule, right? The derivative of x squared e to the x is 2x, the derivative of the first factor, times e to the x, which is the second factor, plus e to the x, the first factor, times the derivative of the second factor, times x squared, which is the first factor. Let's do that again. The derivative of the first factor is 2x, the second factor is e to the x, the derivative of the second factor is e to the x also, and the first factor is x squared. So that's the derivative of the numerator. Then we get times the denominator, x plus 1, minus derivative of the denominator, which is 1, times the numerator, which is x squared e to the x, divided by the square of the denominator. And then it's just a matter of multiplying things out and factoring out an e to the x. I think I probably first multiplied out the parentheses. No, I did both. Okay. We have an e to the x in common here. That comes out. Then we multiply out the parentheses. 2x times x is 2x squared. X squared times x is x cubed. 2x times 1 is 2x. X squared times 1 is x squared. So I typically don't remember FOIL, first, outer, inner, last. I just remember that when you multiply out parentheses, everything in the first parenthesis has to be multiplied with everything in the second parenthesis. And that means with a parenthesis of 2 times another parenthesis of 2, you get 4 factors, 4 summands, and that's what I've got here. And, well, the 1, of course, here is superfluous, so we just get minus x squared e to the x. And we've got an x plus 1 quantity squared in the denominator. That won't change. And so the final result here is that we've got an e to the x that's multiplied out. We get 3x squared minus x squared, that's 2x squared, plus x cubed plus 2x. So it should be what we have here, e to the x times x cubed plus 2x squared plus x squared minus x squared goes away, plus 2x divided by x plus 1 quantity squared. And that's about as good as it gets. That derivative is done. Okay, well, this is it for the product and quotient rules. We've gone through pretty much all the applications that we have for the derivative, all the conceptual things, except for computing concavity, except for graphing, and except for optimization. Graphing of rational functions specifically we'll talk about in the next presentation on the chain rule, because the chain rule allows us to compute the second derivative of a rational function a little bit easier. And I think we'll also talk about optimization when we talk about the chain rule. But for this one, go ahead and just practice the product and quotient rule and then move on. Thanks.